Good evening, ladies and gentlemen. I think just after 6 o'clock, so I think we should start. Just before we get on to the main event, I'd like to draw your attention to some late-breaking news tomorrow. Shenzhou 7, which was the recent manned mission from China, there will be some news and an explanation of this tomorrow morning at 8:30, so nice and early, but please come and see us here. Okay, so welcome to the Climate Day Highlight Lecture here at IAC 08. I'd like to introduce our Climate Highlight Lecture speaker, Professor Alan O'Neill, who is the Director of the National Centre for Earth Observation and Professor of Meteorology at the University of Reading. His research expertise lies in the areas of data assimilation and Earth observation, atmospheric dynamics and transport, and climate modelling. So without further ado, I'll hand over to Alan for tonight's lecture. Thank you.
Thank you very much. And thank you for coming, particularly those of you who managed to drag yourself away from the Astrium beer tent, which obviously doesn't seem to represent too many of you, actually. But never mind. I've changed the title of my talk to emphasize the importance of Earth observation in connection with the challenge of monitoring, diagnosing and predicting climate change. Now, climate change is an issue that concerns us all, but I want to get across the fact that the science behind it is exciting, challenging, interesting and inspiring. I know it's 6 o'clock in the evening and being inspired at this time of day might be a bit difficult, but I shall do my best. I'm from this National Centre for Earth Observation, which is a virtual centre, and what it really means is we're a distributed entity functioning like a centre, and we've been created by the Natural Environment Research Council here in the UK. We got underway in the 1st of April this year. We've got a 5-10-year programme, depending on the generosity of the funding body, and we're involved in many aspects of Earth system science, including climate, earthquakes as well, and Earth observation, along with mathematical models of the Earth system, are the foundation of our science. So let me start you off and put you in the wrong frame of mind by 2 slides, and then I'll take a pause and try to put you in the right frame of mind. So let me read this. You can read it yourself. Climate change has been described as one of the greatest challenges facing the world in the 21st century. The weight of evidence for climate change and the causal link with greenhouse gas emissions, most notably carbon dioxide, is now unarguable, and that comes from the authoritative document, the IAC programme notes. So why do we need Earth observation then? Is it all done and dusted? I don't think so. So the second slide that is fairly traditional in talks like this is something along the following lines. Climate change can be associated with melting of ice sheets, changes in the ocean circulation, sea level rise, changes in patterns of precipitation, intense storms, severe events, production and transport of atmospheric pollution, which moves around the planet, and changes in the distribution of organisms leading to health problems. So there's a whole bunch of stuff there that can get us worried. Now, yesterday I wandered up the exhibition hall over there somewhere, and I was inspired to see some fantastic art from, I think they call the Institute of Astronomical Artists or something like that, and there were some fantastic pictures of the various objects in the universe, and I got talking to one of the artists there, and I happened to spot planet Earth, and I made the remark that this is one of the most complex objects known in the universe, quite awe-inspiring. And it's particularly complex because we're part of it, life is part of it. It's the only object that harbours life as far as we know, and it's our effect on the effect of life on climate and climate's effect on life that is one major part of the complexity of the system. And I was saying that perhaps some of the awe of this had been lost because climate change is coming across as an issue, as it is, and perhaps some of the wonder and excitement of the science has been a bit lost. And she agreed with that, and she said, I've forgotten her name, my apologies if she's here. She said, yeah, she thought the fear factor, these are her words, she thought the fear factor was overcoming the awe. And I agreed with that, and I reflected a little bit on the plenary session on Monday when the directors of the space agencies were up on the podium there. And it was interesting that the tremendous tendency of the discussion was to gravitate towards going to the moon and Mars. And I think that's fantastic stuff, I have to say. I mean, I was brought up as an astronomer, so I love it. However, I think to some extent people in Earth system science need to redress the balance a bit and try to emphasize the wonder and fascination of the science behind these issues that are in the press every day. So that was my feeble attempt to put us back on track. So climate then consists of a continuum of time and space scales, starting from very small convective systems that are very energy intensive. They transport pollution from the low atmosphere to the upper atmosphere. They can form convective clusters that have a strong effect on the circulation through the release of latent heat. Then there are large storms that come across the Atlantic and the Pacific and in the southern hemisphere on long storm tracks, and changes in their intensity under climate change are an issue. We have here in rather schematic form the ocean circulation, showing in bold colour the upper level circulation and the large scale transports of ocean circulation, then sinking of cold water and a return flow clearly connecting the planet, and taking many centuries for this circulation to complete. On much longer timescales, going back 400,000 years, we see changes in methane, changes in temperature, and changes in nitrogen dioxide, nitrous oxide, my apologies. And this is showing that we have a very strongly coupled system where the causality, is it the temperature change that's leading to the CO2 change or vice versa, is still not fully understood. Over on the bottom right-hand corner, we have on centennial timescales, the issues of global warming and the associated uncertainties as a result of greenhouse gas emissions through anthropogenic emissions due to man's activities on the face of the planet. And over here we have the well-known El Niño in the tropical Pacific, which is showing the warming of surface waters in the Pacific region here, and in somewhat schematic form the fact that this change in circulation affects not only the tropics but has an impact on the wider planet. Now the thing about this then is that already we can say and know that many of these scales in space and time are highly interconnected, so it's extremely complex. And the other thing this says to me is it also tells us something immediately about the kind of observing systems that we're going to need to study a complex body like this. We're going to need technologically advanced systems, for example, to study convection in the atmosphere by firing radar and LiDAR beams into it so we can understand the makeup and dynamics of clouds. And these operate on time scales of an hour, so we need very advanced technology to observe these systems. But then when we're looking at much longer time scales, we need observing systems that actually give us long continuity of data so we can understand the slower processes in the system. So it's this mix between the high technology process-related observations that we need, along with long-term data records, which may come, not necessarily, but may come from instrument systems that are somewhat lower in terms of technological advance. I mean, for example, long data records of temperature in central England tell us quite a lot about climate change, at least in this part of the world, over the last century, and that's just from a thermometer. So if we can get very well calibrated instruments and long records of those instruments, then that gives us a very important basis for some of the science that we have to do. So that's a few points to make about that slide. Right. So we're at a revolutionary period in our understanding of planet Earth, and of course this involves human brains, but human brains are being supported by two technological major advances. High performance computing, which is allowing us to simulate aspects of the Earth system, not just individual components, but the coupled system, as we're moving now from teraflops to petaflops and massively parallel systems. And also, very fundamentally, in any physical science, observations are absolutely essential. We can't rely on our computer models, far from it. And Earth observation is from space, and let me emphasize the next bit, integrated with ground-based measurements, are absolutely critical. And we can see why Earth observation from space is providing us a revolutionary view of our planet, because first of all, Earth observations from space, orbiting satellites or geostationary satellites, give us regional detail in a global context. So we can see things that are happening locally, but we can put the changes in a wider context, because the planet, different parts of the planet and different systems on the planet interact with each other. So this is why the satellites are so key in this regard. The satellites provide also homogeneous measurements from space. I mean, one instrument, I know we have many more than one instrument, but one instrument orbiting is giving us continuous measurements as it samples the Earth, and it's just one instrument that is doing it. So it's much easier to deal with error characteristics in that way than it is from a heterogeneous mixture. And the last thing is technology is allowing us now much better spatial, temporal and spectral coverage. We're seeing much more of the electromagnetic spectrum, and that's allowing us to get many measurements of different parameters of the Earth system. And in many cases, it's a combination of measurements, not just one individual killer measurement, that gives us the scientific breakthroughs and understanding. So building on that technology, we need coupled models of the Earth system. By coupled, I mean we have to build mathematical models of the atmosphere, the ocean, the land, the cryosphere, and indeed the biosphere. We need much higher spatial resolution than we've had hitherto to represent the processes that are relevant. And crucially, they must be stringently tested against observations. And this is where this new era of satellite observations is key. And we need refined ways of using Earth observation to test models much more stringently than we have hitherto. One of the problems with climate models is that climate models are not trying to replicate the weather or the ocean state in any particular day. They're trying to represent, in some sense, an average, maybe a 30-year average, typical averaging period of climate research, as well as the variability. So when Earth observation, when a satellite goes into orbit, let's say it's up there for 3 or 4 years, it's quite difficult to use the observation on a particular day, because to compare it with the model is not actually trying to simulate the observations of that day. So we need advanced methods to combine and synthesize observations with models to bring about this more stringent testing than has happened hitherto. And the method that we use are advanced methods in so-called data assimilation, which combine models and diverse data. And this is then a foundation of science-based prediction systems. So these are building a really refined picture of the state of the system as the foundation of a prediction. That's exactly what happens in atmospheric weather forecasting. Satellite observations are a foundation these days of weather forecasting. It's transformed weather forecasting. Satellites, as well as the atmospheric science, has been transformed, and our understanding of the atmosphere by the demands of building an operational capability and having our predictions tested day by day, moment by moment against observations. And that's what we need to extend now to the whole Earth system. Now, the models have got much more sophisticated, apparently, over the decades that the Intergovernmental Panel for Climate Change has been considering the issues surrounding climate change. From the 1970s, climate models really had very limited processes. They had the sun, sure, they had an atmosphere, they had some rain, and they started pumping some CO2 into the atmosphere to look at climate sensitivity. But then we realized that the atmosphere had clouds, so we better represent those. We didn't have a very sophisticated treatment of things like ice or the ocean, so we just specified the state and didn't allow it to interact with the rest of the system. Then we said, well, hang on a minute, the ocean is a very strong reservoir of heat. We better get that on board. It's like the flywheel of the climate system. But the ocean representation was quite primitive. It was really a swamp rather than an ocean. This far means the first assessment report of the Intergovernmental Panel, and so on. Then we have volcanoes, and we then get a bit of an ocean circulation. And then we have better representation of the ocean circulation. We then try to represent the carbon cycle, not just the anthropogenic man-made part, but the bit associated with the natural ecosystems on land and in the sea, and so on. And now we're getting into atmospheric chemistry and the feedback between climate change and air pollution. And that's all very marvelous, but what is certainly the case is that this evolution in complexity does not mean that as we move from one square to the other, all the problems and issues associated with, for example, rainfall have been cracked. Far from it. We've recognized the need for greater complexity, but in putting greater complexity in place has often led to much greater problems in our understanding as the different systems interact in unexpected and unknown ways. So now let me move on. This is rather a complex slide, but there's a key point to make. Let me now move on to how we are using Earth observation to test models stringently and to show up some of the model issues we have to overcome. By the way, the models are the foundation of our knowledge of the Earth system. They represent our best understanding as embodied in the mathematical models. That is not to say they're perfect, and what I'm doing in pointing out model deficiencies is simply saying, yes, there are model deficiencies that need to be overcome. This is not a recipe for climate skepticism. This is saying what all people associated with the Intergovernmental Panel for Climate Change know, that there are some predictions that we now think are robust and others that are far less robust. So this is now showing the A-train, the Calypso, CloudSat and Calypso satellites, which are radar and LiDAR on the NASA A-train. And these are active instruments. They shoot beams into the atmosphere. And along a track, this is height 0, 5, 10, 15, 20 kilometers through the atmosphere. You don't need to worry about the details. From this information now, we're obtaining the amount of liquid water or ice water in clouds along the viewing track of the satellite. And then we get the same thing, in this case, from the Met Office's operational forecasting model. Now, the forecasting model has been put in a state such that it can make a direct comparison between what the model thinks is there and what is being measured. Now, the reason I'm emphasizing this is one of the greatest uncertainties still in climate prediction is the feedback between clouds and radiation and warming temperature. So the cloud radiation feedback remains a big issue. We don't understand it completely, far from it, and our models have significant deficiencies. So if we use the data, we can make a direct comparison, and we can then do many orbits of this comparison, and we can build up some statistics that actually show in some detail where the problems are. Now, I haven't got time to go through this in too much detail. Suffice it to say, along this scale is a measure of the ice-water content of clouds, so how much ice is in the clouds. And this is some measure that way. And up here is the temperature, so from -10, -20, -30. So broadly speaking, going up from the ground up into the high atmosphere. And this is from CloudSat and Calypso. And now this is from the Met Office's model, which is the foundation for their climate model. And you can see, well, this curve here is a physically constrained curve. I won't go into that. But you can see there's a very significant difference in the kind of scatter and spread. And I could spend quite a bit of time on this slide, but one thing I'll point out here, for example, is that this slide indicates that there is much more cirrus cloud in the real world than there is represented in the climate model. And this is very important because cirrus cloud is one of the important ingredients in understanding cloud radiation feedback. So this is just one example. Let me go to another. Here's an example now of what we've seen using Earth observation and since 1950 all the way through to the present of the cover of Arctic sea ice. And these are different, I won't go through all these panels in detail, but these little panels are different models, representation of ice coverage. Forget the right-hand side. What you can see, however, is this is what we think, this is what we measured to be there, and you can see the decrease, and this was 2007. The blue area is the projected spread of predictions from climate models. And so what you can see is that certainly 2007, and indeed now 2008, is outside the range of variability. So it is true that the climate models are predicting a significant lowering of Arctic sea ice, but not for some time yet. And so this seems to be happening quite a lot sooner than the models have predicted. It could well be, of course, it goes back, what happens next summer or the summer after, the red goes back into the blue, but that remains to be seen. What this is saying to me is that we're not representing in our models the real variability of the climate system, the ocean processes, the sea ice, and the atmospheric processes well enough to capture the variability that nature has, which obviously gives us concern then about the use of these models for prediction. And also, we're not just concerned about the Arctic because of the polar bears. I mean, that's important. Let me not underestimate the importance of the Arctic for ecology. But we're also concerned, of course, that the Arctic is coupled, for example, through the overturning ocean circulation through the rest of the climate system. So this is really a big issue, and this is just another example of why we need Earth observation to have a reality check on the models. Just to go on, in this similar vein, this is showing for the planet the level of skill that models have now in replicating aspects of vegetation on the land. Now, vegetation is important for obvious reasons in agriculture, but it's important for the climate system because vegetation affects the albedo, the amount of sunlight that's reflected back into space. Vegetation is also important because it's part of the natural carbon cycle, and we're concerned about changes in the natural cycle and whether these changes could exacerbate what mankind is doing through its emissions. And so we're not very comfortable when we find measures of skill which have low skill in the models, as indicated in blue. There's rather too much blue for comfort. Now, there's another story that could be made about the ocean, of course, because the ocean is also part of the natural carbon cycle, both in terms of take-up of the ocean and emission. But that's good enough for the moment to say, well, we've got some work to do there. This is particularly difficult, this area, because our knowledge of the processes involved and our modeling capability for ecosystems and vegetation on land is really not well developed. And I think the challenge is going to be to use Earth observation to get the science much more developed so that we can then represent the relevant processes much more fully in climate system. By the way, the carbon cycle is strongly coupled to the hydrological and energy cycles. So you can see we have got a problem on our hands here. Let me move now on to an area I want to pick up a bit more detail about the possibility of regional climate prediction. Okay, fine, we can make projections into the future about global climate change, and we can have a pretty good stab of saying that the temperature changes are greater at higher latitudes because of the ice albedo feedback effect. If you don't know about that, don't worry. Just that there are basic, robust feedbacks that we think work in particular ways. But then what about regional? If we really are going to implement strategies for adapting to climate change and for planning how we manage our resources, then we really need to think about not just global climate change out of 2100, but regional climate change on shorter timescales, such as decades. Now, this is straight out of the fourth assessment report of the IPCC. I could have shown something similar for other areas of the world. I just chose South America. And what we're looking at here is the temperature change projected by a group of about 20 climate models, projecting the change from the end of the last century, the 20th century, to the end of this century, the 21st. And what we have is annual here, December, January, February, which of course is southern summer, and June, July, August, which of course is southern winter. And the temperature response, I won't go through this in too much detail. We're talking about a few degrees warming as indicated here. Now, if we now look down at the response to precipitation, basically rainfall, and the changes, what we're seeing is, in brown, changes of about 20 or 30% as projected over this century. And again, this is annual mean, December, January, February, June, July, August. And you can see, for example, here, that the average from all these models is saying something like, well, what, 15, 20, maybe 30% over Amazonia in June, July, August. Now, the bottom diagram is a little bit complicated, but it's actually telling us about the degree of agreement between the different models in this projection. It's a rather funny diagram, the way the numbers work. But let me just help you by saying that essentially where areas of white, roughly half the models say the precipitation change is going to have one sign, let's say wetter, and half the models say the other sign, let's say drier. So if we look here, for example, where on average the models are saying, well, 15, 20% drying over this region, then about a quarter of the models are actually saying it's going to get moister. So you can see we've got some issues there, and undoubtedly these are issues and not just about the climate processes happening locally in South America, but it almost certainly involve the land process, ocean circulation, and the broader climate. Now, a very important part of climate system is the fact that it's chaotic. There are elements of the key elements of the climate system that are chaotic. And we need to learn how to put our finger on those bits of the climate system, particularly on regional scales, that are predictable, and those that are basically noise, some of which may be unpredictable. And a classic illustration of this is this kind of pinball machine, where let's imagine as we drop the ball bearing, it bounces around on these pins, and we do this many, many times. Each experiment of dropping the ball could be regarded as one evolution of the climate system over the next several decades. And what we'd end up with then is a distribution of balls, and we could say, okay, well, the mean temperature is so-and-so, but there is a spread. And of course, what we'd like to do is narrow the uncertainty. We'd like to make sure that this spread is not associated with lack of knowledge or problems in our models, but is in some sense pinned down to being the irreducible spread connected with the natural climate chaos of the system. That nature has given us, and we just have to live and bear it. Now, when it comes to climate prediction, we might be helped actually by the fact that climate has memory. What do I mean by that? Well, if we put greenhouse gases into the atmosphere, and those gases stay there for, say, decades, as we believe will happen with CO2, then there can be a bias in the climate system. What that means is that the spread that we had before when we dropped the ball bearing is skewed, it changes. So climate change is not just about the change in the mean position of where the ball bearings end up or where the temperature ends up, but also about the extreme events. So in this case, for example, we have many more events over on this side of the pinball table than on the other side. So this could be the damaging storms, for example. Now, another aspect of climate having memory is that there are slow processes in the system. The ocean is the classic one, where if we can build up knowledge of the deep ocean circulation and capture that in our models, that might lend some predictability to climate. Forgive me, by the way, my voice is, I've been talking far too much today and my voice is kind of caving in. So we do have this issue we have to contend with, the natural noise of climate variability. But let me say a bit more then about the technology and where we're going. Many of the processes we have to deal with, the atmosphere, I've shown that schematically earlier on, the ocean circulation, some of the schematics really don't do justice to a longer talk where I could have shown much more evidence for the fluid flows in the system and the small scales that we have to represent. It's not that the small scales that we have are trivia. The Gulf Stream, for example, that flows up the coast of on the eastern seaboard of the United States is about 100 kilometers wide, but transports huge amounts of heat. So capturing those details is critically important. And in the past, our climate models have had rather crude spatial resolution. Here's a former version of the Hadley Center coupled atmosphere-ocean model with resolution as indicated here. A few grid boxes cover the whole of the UK. And the ocean circulation was also limited by poor resolution, so that some of the analog of atmospheric weather systems in the ocean, so-called mesoscale eddies, was not being properly represented, and that has an effect on the ability of these models to capture the heat and salinity transports, the salt transports in the models. But now there's a very big push to much higher resolution where we capture these details, and of course high-performance computing is helping us. The Earth simulator in Japan is a very nice example of where the technology is being used to get very fine resolution for climate prediction. And I think this is going to be a strong driver in the future, but it's not all about modeling. It doesn't take us away from the thought process. It doesn't take us away from the need to hammer these models with observation and to beat down the errors that, even if we go to high resolution, won't magically transform the misrepresentation of some key processes. The world of computational fluid dynamics is evolving tremendously. We're getting now very sophisticated ways of representing fluid flows on the planet. The atmosphere and the ocean will be classics. Some of these advances have come from completely different fields, for example, explosions and various other applications in industry, which we can now apply on the sphere and then have high resolution in particular regions of the globe where we have fine scale structure that needs to be represented, so we adequately represent the processes. So this technology of computational fluid dynamics is also making big inroads, and here's an example of where we can refine the grid to capture, in this case, a coiling atmospheric eddy, and the same approaches are being used in the world of oceanography. So this is, again, a major scientific advance being aided. We couldn't do this without high-performance computing. So now let me move on to the world of Earth observation a bit more and highlight some generic challenges for Earth observation, which I can just touch on briefly. First of all, we have a real challenge of how to use satellite measurements optimally. Now, the point is, of course, satellites don't measure temperature. They count photons, for example, nor do they measure parameters that models have, nor do they measure parameters on the model grids that I was illustrating earlier on. So there is a translation job to be done. We've got to find a way of comparing apples with oranges, but really making apples comparable with apples. And that's a very challenging exercise. We know how to do it, in principle at least. This is this technique I've mentioned without describing, mercifully for you this evening, because it's rather long-winded and excitingly mathematical. Not that you couldn't cope with it, but today's too late for that. So that's one job we've got. Another key task is acquiring long, sustained, well-calibrated data sets. I'll illustrate that in a minute. If we're going to represent and understand and figure out why we've got long-term trends, or by long-term I mean decadal, over decades, and pin those trends down to natural or anthropogenic processes, we clearly need a long data record that we can, even if it's not one instrument, we must be able to stitch the record together so that any jumps in the record are not artifacts of changes in instruments or methodology of processing, but genuinely represent jumps, if there are jumps, in the natural system. And as we gather more and more Earth observations, and as we build our models and our ability to assimilate the data into these models, by the way, this word assimilation is not kind of something from the social sciences, with all respect to the social sciences. It's very precise algorithms that combine models and data, making allowances for the known or supposedly known errors in both the models and the data. That's all I'm going to say. But what we can do is we build up decades of data, as we are now doing, is go back, use modern methods to reprocess old data, and really that illuminates tremendously the changes in different parts of the Earth system and gives us a real handle on what's been going on. I mentioned the need for Earth observation to test models stringently and to remove model errors. That's absolutely critical. I mentioned earlier on the idea that we're moving to a phase, particularly when we come to shorter timescales and more regional predictions, where we need to get now accurate understanding and knowledge of the initial state of the Earth system, not just less so of the atmosphere for reasons that some of you will be aware of, but more particularly of things with long memory like the ocean, the land surface, the ice sheets. Because without that, we really have got very little hope of making good predictions on decadal and regional scales, and in many ways to manage the twists and turns of climate change. This is precisely where we need to go now. IPCC has been emphasizing the climate change out to 2100, and that's been very important, and that's alerted us to the significant issues. But IPCC has also noted now the imperative is to move towards the decadal and the regional. That presents an enormous challenge where Earth observation comes center stage, because now, without the Earth observation to set up the models in accurately representing the state of the planet now, then we're really going to pull the rug from under our feet in terms of these regional decadal predictions. And last of all, then, we are building, if you like, an Earth management system out of this, developing from these models with the data a whole range of additional models, for example, with predictive skill that key into the bigger models, to develop integrated information services for climate and environmental needs. So long-term data are critical then to identify cumulative effects of slow processes. This is 1994 to 2010, and this is showing CO2 increase. The grey is from Mauna Loa, the volcano in Hawaii. But now satellites are coming along, and they're giving us measurements that tie in well with the ground-based measurements. Satellites do something else. They tell us what the CO2 is like around the world. And if we can make very accurate measurements, then we might be able to see where the CO2 is being emitted and where it's being taken up. not at factory level yet, but certainly on a regional detail and in some aspects of the ocean. And so we need long-term data to identify cumulative effects of slow process, to identify related trends in the Earth system for scientific understanding and attribution, and to enable prediction, identifying changes that can be extrapolated. So that's the CO2. Another quick example is ozone. This shows from 1975 to the present the area of the ozone hole over the Antarctica, and satellites now have been enabled us to monitor the opening up of the ozone hole. They were fundamental to allowing us to understand the nature of it, and that it was indeed man-made chemicals that did the dirty business over Antarctica. And they'll be able to tell us whether or not the remedial action that the world has instituted to take out the damaging chemicals and to put in replacements are going to work. So this is showing the ozone hole opening up, and who knows, with any luck, it'll start to close as the chlorofluorocarbons are flushed out of the system. So now we've got altimetry as well, giving us information about sea level rise, and as the altimeters can be stitched together, we're now building up a nice record showing the overall trend. And by the way, this trend, as now being measured, is on the upper bound of what is being predicted by some of the climate models. This is the global mean sea level. What the altimeters are also going to give us, and are giving us, is the regional detail, because sea level rise is not uniform around the world. The ocean is in motion, and that has a bearing on where the sea level rise is greatest. Now let me pick up this point about satellite data inhomogeneities and the need for careful calibration between satellites. This is thanks to Craig Donlan. He doesn't know I've actually stolen this from him, but he's not here to complain. So this is a time series from the microwave sounding unit, which is on the operational weather satellites. I could have shown this, by the way, for things like the total solar irradiance, in other words, the measurements from the sun, which we need to calibrate very carefully. And I could have gone on, but this is a good one to show. And this, just over a couple of decades, you see, first of all, the temperature variation this is the signal, this is the real world, so this is the seasonal climate variability. And then we see the individual satellites, and there clearly are drifts on the individual satellites, and those drifts are to do with drift in the orbit as it comes across the equator, and degradation of the instrument. And we see problems about calibrating one satellite next to the other. And of course what we're after is the slower long-term trend and our ability to pin down and attribute that trend. So you can see how essential it is, if we're trying to back out the trend, how careful a job we have to do in matching up the individual data records from individual instruments. And this will not happen in the margins of operational weather forecasting or operational anything. It's got to be a really concerted effort to bring this about. And I'm glad to say in this regard, I may well be unaware of other initiatives, but the European Space Agency, I'm pleased to say, are stepping up to the plate in this regard and are proposing an endeavour to make sure that the satellites, particularly connected with GMES, do have this extra ingredient to allow us to stitch the instruments together and build up what will hopefully become, besides its other role, in effect, a climate observing system. So here's the problem we've got then when we're dealing with climate. We've got very small scale processes that we have to represent. So that's the high resolution aspect. We've got the complexity. We've got the fact that the systems are highly coupled. For the technical amongst you, probably all of you, highly nonlinear. You double some forcing, you get 4 times back what you put in. And we've also got the fact we've got chaos in the system, so we can't just integrate or run out our model projections, just one of them. We have to do many and build up this probability distribution of what the outcomes are. So we've got a real problem with our computing resources to get the right balance between complexity, resolution, and the number of members in these integrations, so-called ensemble size, that we have to do. But then along comes now, when we come to decadal and seasonal prediction, so timescales, say, from 6 months, running out to decades, the kind of seamless operation from routine weather forecasting to now climate predictions on regional and decadal timescales. Here comes the other big challenge. The fourth dimension to this is the world of data assimilation. This is the challenge of synthesizing diverse measurements from different platforms with a model to provide the foundation for prediction, and in the process for stringently testing the model. So it's a double benefit. We build up the capability to get predictions with measures of uncertainty in those predictions, and at the same time we're hammering the model with fresh observations on a regular basis. So let me move a little bit to the particular challenge. I'll have to just make a few points here and accelerate a little bit my talk this evening. I got carried away at the beginning. We're talking about the astronomical art, I'm afraid. So the challenge then is to develop quantitative risk-based predictions of the future state of the climate and climate impacts on regional, local scales, especially for the next few decades with measures of uncertainty, right? So that's the spread. We're not making what is called a deterministic forecast. Now, there are several things we've got to sort out. We've got to identify some of the causes of uncertainty in these decadal climate predictions. First and foremost is model uncertainty. And so different models simulate different changes in climate for the same kind of external forcing. So that could be part of the misformulation of certain models. There is the noise of natural internal climate variability. And of course, in terms of longer-term climate change, there is the uncertainty associated with the emission, anthropogenic emission, and what legislation and political considerations do, if anything, to limit that. So there are a whole bunch of uncertainties there that we have to deal with. And I'm just tempted to pause a bit on this. Let me make a quick decision. I won't take you through this slide. I don't have the time. Suffice it to say, if I were to take you through this slide, courtesy of Rowan Sutton, which I don't have the time to do, the message is the following. When it comes, there's a lot of lines on here, it'll just take me too long. I just want to give you the bottom line statement. It's this. When it comes to predictions on decades, we are now being held back very significantly by two things. One is the uncertainty in the model formulation, difficulties and problems with our understanding of processes and our representing of those processes. And secondly, our knowledge of the initial state of the system. When we get way out here to say 2100, in the original IPCC domain, the biggest uncertainty is the scenario, which is basically the amount of CO2 that's being emitted. So that again is where Earth observation comes in. Let me just emphasize this. Now, when we move away from the biggest uncertainty being in the scenarios, what's happened to this cursor? We're coming back into the near time frame. The biggest uncertainties are related then to model uncertainties and initial condition uncertainties, and Earth observation is absolutely essential, satellite and ground-based integrated observing systems, to deal with those issues, to give us the regional detail and the measures of uncertainty on the decadal timescale. So that's the key message. This is a slide which I'll skip over, showing basically the kind of emulation of what we do in operational weather forecasting. We have climate observations. We set up the initial conditions. We have projected changes in external forcings, for example, CO2 emissions, either anticipated or guessed or whatever. And then we make climate predictions. And these predictions are ensemble. We make many runs at it, and we produce a probability distribution. And one way we can build trustworthiness in decadal climate predictions now is by going back over past data and running decadal predictions from, let's say, 1970, when we're starting to get seriously good satellite data, and we can test out our models against former data. This shows the value now of building up this long data record, and the value, we've hardly tapped this so far. The science is still relatively young. We've got a huge way to go to capitalize on the past data, let alone the data of the future. And there are huge opportunities coming up. Regrettably, I don't have time to go through these in detail. We've heard about GMES Copernicus. There are also major satellites about to be launched. For example, the Orbiting Carbon Observatory from NASA and GOSAT from JAXA, making measurements of atmospheric carbon dioxide, which is going to help us to pin down, we hope, the processes that affect the natural cycle of carbon dioxide and other greenhouse gases in the atmosphere. And I could go on. One thing I'll just touch on quickly, because I will draw to a halt in about 3 or 4 minutes to give some time for questions, is the satellite that's just about to be launched. I think it was originally going to be launched on the 10th of September. Now I think it's been delayed. I'm not quite sure. Maybe it's next week. I'm not sure. Somebody can yell at me when it's scheduled to be launched now. GOCHE, this is an ESA satellite. It stands for Gravity and Ocean Circulation Experiment. And there's a NASA satellite, GRACE. And I want to pick up this as one example of a profoundly new measurement, which tied in with other measurements, altimetry, satellite altimetry, that we've had for some time, is going to give us now really unexpected advances in our knowledge of the ocean circulation. So of the many things I could describe on this slide, not least, incidentally, the importance of ground-based measurements and measurements in the ocean. So it's not all satellites, in case any of you are wondering. Let me just skip a bunch of stuff to pick this one aspect. Oops, I seem to have lost a slide here. I have lost a slide. Right. The slide I was going to show you, which I'm now embarrassed to admit I don't have, but I can still bore you by talking, because I'm quite good at that, would show you how GOCHE is going to give us a measurement of the geoid. Now, the geoid is an imaginary surface of equal gravitational potential, so of equal force of gravity, if you like. Now, when we don't have a good and accurate geoid at the moment, and if we knew the geoid, and if we know the position of the ocean surface, which we can get quite accurately to centimeter accuracy from altimeters, we can put those two things together. Ah, there's the slide. That's what I was after. Where did that go? Okay, this is not GOCHE, but this is the kind of where's that cursor gone again? This is the altimeter, and this is showing the altimeter in orbit, shooting radar beams down at the ocean circulation, and we, through laser ranging and all the rest of it, we can figure out where the ocean surface is. Now, the dashed line, and I don't know what's happened to this cursor, the dotted line, is the so-called geoid, and we can get that now with GOCHE to centimeter accuracy over scales of about 10 kilometers horizontally. Now, the geoid rises and falls by about 200 meters. Now, if we know the geoid and we know the height of the ocean, we can go further than knowing just about the height of the ocean. We can get at important information about the ocean circulation. And then we can assimilate that new data. We can go back and reprocess all the altimetric data, all the height data, and look at the ocean transport of heat and salinity, and synthesize it, estimate it over decades. And this is the example here, the black line. The blue line shows what the model had naturally, in other words, significantly representing the variability. And the dots are actually transects from a ship. So you can see that the altimetry now and this is not GOCHE yet, but it's a synthesized attempt at GOCHE. So I won't go into the details of that. But we get good match up with the measurements. But the big thing now is that when we've gone and reprocessed all the data, we can see much more clearly the variability. We can understand much more clearly the natural variability of the system, and we can say intelligent things about trends. We may not be saying intelligent things about trends if we took two data points and said, well, the ocean circulation is shutting down, isn't it? Well, no. And last of all, and then I'm going to conclude, I want to go back to the point I was making earlier on at the beginning of my talk about the mix between high-tech, advanced satellites to give us a profound new picture in quantitative terms about key Earth system processes and the need for long-term measurements. This is Cryosat, another ESA satellite. You will obviously be aware of my European bias in some of these selections. I must say the UK has benefited enormously from its scientific interactions with NASA and JAXA and increasingly with other space agencies, so forgive me for the slight ESA bias in this talk. Cryosat is like a bat in space. It chirps out a radar beam and it's got two ears which takes the signal and it gives very high resolution. It gives us very high resolution picture of ice margins, so we can look at ice dynamics as well as on Greenland and Antarctica. Very important for understanding the changes in ice attendant on climate change and making quantitative estimates of how continental ice will change and indeed how good our models are in representing that. And also of the sea ice extent and so-called freeboard, the ice thickness. Now this is great. We need very high-tech instrumentation to give us this handle on new ways of looking at the planet, new quantitative measures that we didn't have before. But I hope I'm not saying anything politically incorrect here, but clearly we need things like cryosat in perpetuity. How can it be one-off? This technologically advanced satellite today, one assumes, will become, to use an English expression, the bog standard operational satellite of the future, one hopes. So this is just an example of the constant evolution of technology and how today's demanding technology and advances that we can make can then become kind of technological commonplace, but give us the vital long-term information that we need. So, conclusions then. EO from space is of central importance for climate research as part of an integrated observing system, including ground-based measurements, aircraft as well, for monitoring diagnosis of climate change, environmental change, and initializing, that is, setting the initial conditions for and testing models. And I've emphasized the need for well-calibrated long-term data sets, and the term that people use commonly are so-called essential climate variables. These are key measures of the health of the planet, like the temperature of a human being, or the pulse rate, or some measure of lung capacity. It's the same thing. That's exactly what we need, and we need to ensure that the trace that we get at the foot of the patient's bed is not that the nurse or whoever is doing it is going to slip the pen through some artifact in the data of processing, but is really a well-calibrated record. So I think the system that we're describing here should comprise innovative new measurements, pushing the technology forward to give us the scientific breakthroughs that we need in understanding, with sustained old measurements, I've said there, but what I mean by that is we can make, I think, if we need to, technological compromises, if we need to have robust, relatively cost-effective systems in place to give us long-term measurements. And it's not the case that we always need fancy new measurements to do great new science. New science can be done by virtue of the length of a data set. If we've got a long-term data record, it can tell us a lot about the relevant processes in the Earth system. I think my last penultimate point, I would back off a little bit from this now, I think. At one stage, I felt a bit concerned that there seemed to be no operational climate observing from space planned. I think we don't have one in place, but I have a sense now, increasingly, internationally, we're looking now to see whether we can build on the capability that may have been deployed for other purposes, whether it's operational weather forecasting or the original conception for GMES, and to develop that functionality and give it and enhance that self-same functionality to give us a double benefit, the operational benefits that flow from sustained measurements, as well then as the climate observing system that is so vital to understanding and predicting climate change, and therefore being able to adapt to climate change. And I think I'll close by saying I'm glad to say that Copernicus GMES has the potential, I think, to be a key component of an Earth management system. And that's it, and I won't bother you with that, which would be something about the institute I'm involved with. Thank you very much. Okay, we've got 5 minutes for questions, I'm told, so if there are any climate skeptics out there and you want to have a go at me, or indeed anybody else, I'll do my best to answer questions.
Thanks very much, Alan. So we have a roving microphone here at the front. We have some microphones as well in the corridors there. So who's got the first question here on the right here? Thank you.
Dick Klein. I was very impressed by what you had been saying there. And earlier, we listened to a GEOS presentation, which seemed to be formative of putting things together, I suppose, to be of service to you and your associates. My question comes back the other way, and that is to say that are you and your associates going back and in a prioritized way telling those people what you would like to see in order to make a better model?
I think that dialogue is taking place. I think there's a lot more communication that needs to be done, and I think there are lots of issues of prioritization that we need to establish. I think things like GEOS are providing us an international context that we can actually coordinate the effort internationally. It's clearly an international effort. And I mean, the simple answer to your question is yes, that is happening. More of it needs to happen. And clearly, with the challenge, the cost, the scientific and technical demands, it's absolutely essential it does happen.
Thanks very much. Next question. Here on the right as well, then. Thank you.
Hi, I'm Bill Nye, Vice President of the Planetary Society. Is there any reason to think that we won't be at least 4 degrees Celsius warmer worldwide than we are now by, let's say, 2060?
What's behind? Is there something behind your question, or?
Well,
I mean,
these data are astonishing. I mean, it's very impressive how much accuracy you have now. But is there any reason to think that the world is going to slow down? Are we going to be able to reduce greenhouse gas emissions, let's say 80% by 2050, 2% a year?
Well, I'm not a politician. I think to do that reduction is, of course, a technical and exercise, but it needs to be stimulated by the politicians. I'm not quite sure what will happen in that regard. So I don't know the answer to your question, simply put, because it's a societal question as much as a technical one. What I would say, and I'll say this, I think what could be quite interesting and quite a challenge for us in scientists and communicating science to politicians, and forgive me if this is not quite answering your question, but it puts another side on it which might be worth mentioning. It's this. Well, we've seen a global temperature rise over the last decade or so, quite rapid actually. What will happen? What likelihood is there that over the next decade there might actually be a temperature decrease, perhaps something that would occur as a result of natural variability? There is natural variability in the system. We could quite easily, well, when I say easily, I don't have a quantitative probabilistic measure of this, so this is a qualitative statement. We could end up with, as a result of natural variability, a global temperature decrease. Wait a while, I mean, one assumes, if the models are correct and the projections are robust, that that decrease would be temporary and we would then be back up on the general upward trend. But it's going to be quite interesting how the dialogue will evolve if we have, let's say, a decade of global mean temperature decrease. Now, I'm not predicting that, but I don't actually think that's outside the bounds of possibility.
What would you say that possibility is?
I couldn't give you a quantitative measure. So if I were to say something utterly qualitative, I'm not to be quoted, right? If you're a journalist, don't quote me, because it's not. This is not scientific statement. I wouldn't be surprised. There we are. But I couldn't say quantitatively. I think we don't know. We haven't done the experimentation. We haven't done the work yet to give a serious quantitative measure on this.
Okay, thank you. Next question. Just here on the front, please.
Climatology is switching from a research topic to an operational topic, and as usual, the difficulty is to have operational sustained measurement. What is the difficulty to consider that climatology should be in the future part of the mission of the present weather services?
I think if I understood your question correctly, perhaps I could try to repeat it, and if I've got it wrong, you can correct me. Are you saying that what you'd like to see now is, what is the prospect of taking, if you like, a climate forecasting system and making that, and the climate information coming from that, a routine operational activity in the same way as we've experienced this in ordinary weather forecasting? I think there are very exciting prospects for that to happen. We've seen significant steps in that regard around the world. For example, in seasonal forecasting, where we're looking 6 months ahead. On that timescale, we have to represent actually many of the key processes that play a part in longer-term climate prediction. So much of the infrastructure at the leading operational agencies is being developed in terms of the ability to gather the data, the assimilation systems, and that kind of infrastructure. And I think that's happening in a number of countries. Now, what I would say is it's one thing building the infrastructure and the technology. It's another thing making sure that the science foundation is absolutely solid so that the science behind the apparent capability to make predictions is really robust. Always we're going to need measures of uncertainty, and always we're going to be trying to beat that uncertainty down or narrow it to the point that it's irreducible and associated with the physical system in some sense. So I think it's I think the prospects are very good, and I think it's also this challenge. Some people have used the World Climate Research Programme has used the term seamless climate prediction. I think this challenge is galvanizing the scientific community, and it's one example of many where an operational challenge is not some tedious job from a scientific point of view. It's actually challenging the scientists in a way, in a very demanding way, in perhaps ways they wouldn't have been challenged had they not entered that particular game.
Okay, thank you, Alan. I think we should take one last question, given time. So if there's any other questions? Yep, final one here at the front. Sorry, Chris.
Let me rephrase that. Is there any reason, any scientific reason, that we all shouldn't be panicked about climate change?
Panic is an emotive word.
Okay, yes it is. Okay, very, very concerned.
I think we should be very, very concerned. But I think very, very concerned. Like in other, I mean, it's just a personal view. I'm not representing any institution in making this personal view. There are many things in life that make us very, very concerned. And we can either be very, very concerned and just remain in that state, or we can do something about it. And there are a whole range of activities that we can put in place to translate into very, very concerned to let's do something about it. Some of those are political, and that's for the politicians to worry about, informed by the best science, and some are for the scientists. I think, may have sounded rather grandiose language, but I think we're developing the scientific and technical capability now to develop what I've used, terminology rather grandiose perhaps, an Earth management system, or to mimic the GEOS logo, the Earth Management System of Systems. This ability now to develop the tools to monitor what's going on, to figure out why it's going on, and to then make predictions that allow us to get the best cost-effective remedial action. And that's all I can say. I mean, it's just a question of getting off our backsides and doing something about it. And to me, that helps me stop worrying. Don't know about you. It does me.
Okay, thank you very much, Professor O'Neill. I think it's been a fascinating presentation with a lot of excellent information and some real science as well, I think, tonight. So that's been really, really good. I think one point I just wanted to make was some of the challenges you laid down for some of us here in the global space industry. I think we're really interested, and we now need to respond to that. So I think, can we finally take some appreciation for your contribution today? Thank you, Professor O'Neill.